A black hole is not an object with a surface like a planet, and it is not simply empty space. It is a region where mass is concentrated so extremely that spacetime itself is curved in a way that creates a one-way boundary. That boundary is the event horizon. Once anything crosses it, not even light can return to the outside universe. This is why black holes appear black. No light from inside the horizon can reach us. But outside the horizon, a black hole still influences nearby matter exactly through gravity, and that influence can be measured. So black holes are invisible in direct light, but not undetectable. The key idea to hold from the start is this: black holes are predictions of gravity theory, not science fiction exceptions to physics. They represent what happens when gravity is pushed to its extreme limit. To understand why black holes exist in theory, we need Einstein's general relativity. In this framework, gravity is not treated as a force pulling across distance in the old Newtonian sense. Instead, mass and energy curve spacetime, and objects move along paths determined by that curvature. If enough mass is packed into a small enough region, spacetime can curve so strongly that all future paths inside a certain boundary lead inward. That boundary is the event horizon. Importantly, general relativity predicts this mathematically. Black holes are not optional add-ons. They emerge naturally from the equations under realistic conditions of extreme collapse. In that sense, the concept is conservative, not exotic. It is our ordinary theory of gravity applied to extraordinary density. People often imagine crossing an event horizon as hitting a wall or triggering a visible flash. In classical general relativity, neither is required at the crossing itself, at least for a sufficiently large black hole. Locally, an infalling observer may notice nothing dramatic at that exact boundary. The event horizon is defined globally. It marks the limit beyond which return to distant observers is impossible. That makes it a causal boundary, not a material shell. The drama appears in communication, not necessarily in local sensation. Signals sent outward after crossing cannot escape. To outside observers, infalling clocks appear to slow and fade due to gravitational redshift, but this visual effect is about what distant observers receive, not what the infaller experiences in their own frame. This distinction is essential for avoiding common misconceptions. General relativity also predicts a singularity at the center of an idealized black hole solution, a region where curvature becomes formally infinite. Physicists interpret this carefully. Infinite values usually indicate that a theory has reached its domain limit rather than that nature literally contains infinity points in a naive sense. So the singularity is best viewed as a signpost. Classical gravity alone is no longer enough under those conditions. A full quantum theory of gravity would likely replace that classical singular behavior with a deeper description. Still, for most astrophysical questions, we do not need to know the exact interior endpoint. Observable behavior, including orbital dynamics, accretion, and wave emission, is dominated by the spacetime outside the horizon, where general relativity works extremely well. The black hole idea has a long history. In the 18th century, thinkers already considered bodies whose gravity could trap light, though in a pre-relativistic framework. The modern foundation arrived in 1916 with the first exact solution to Einstein's equations describing what we now call a Schwarzschild black hole. For decades, many scientists treated such solutions as mathematical curiosities, partly because the physical interpretation was not yet settled and observational evidence was lacking. By the late 1950s and especially through the 1960s, theoretical work clarified that black hole formation is a generic outcome of gravitational collapse, not a mathematical trick. That shift was crucial. Black holes moved from speculative geometry to expected astrophysical objects. The question then changed from can they exist to where and how do we observe them? The first widely accepted black hole candidate was Cygnus X-1, identified in 1971 through independent analyses. It was not discovered by seeing a black disk in a telescope image. Instead, astronomers inferred it from a binary system, a visible star orbiting an unseen companion with too much mass to be a neutron star and no normal stellar light of its own. X-ray emission from hot, infalling matter provided additional evidence. This inferential style remains central in astrophysics. We often detect black holes by what they do to nearby matter and light, not by direct optical appearance. Cygnus X-1 marked a turning point because it connected theory, orbital measurement, and high-energy observations into one consistent physical picture. From there, black holes became part of mainstream astronomy. How do stellar black holes form? The standard channel begins with a very massive star. During most of its life, outward pressure from nuclear fusion balances inward gravitational pull. Once nuclear fuel is exhausted, that pressure support collapses. If the remaining core is massive enough, no known pressure mechanism can halt the implosion. The core contracts beyond neutron star stability and continues inward until an event horizon forms. At that point, a black hole is born. The exact mass thresholds depend on composition, mass loss, rotation, and explosion dynamics, so nature produces a distribution rather than one fixed cutoff. But the central principle is robust. When gravity wins decisively over all pressure sources in a compact core, black hole formation is a natural endpoint of stellar evolution. Once formed, black holes can grow. They gain mass by accreting gas, capturing stars, and merging with other compact objects. Over cosmic time, repeated feeding and mergers can build supermassive black holes containing millions or even billions of solar masses. These giants are now believed to reside in the centers of most large galaxies. Our own Milky Way hosts Sagittarius A*, with a mass around 4.3 million suns. The growth pathways are still actively studied. Some supermassive black holes may begin from stellar mass seeds that grow gradually, while others may originate from direct collapse of massive gas clouds in the early universe. Different channels may operate in different environments. What is clear is that black hole growth is deeply tied to galaxy evolution, not an isolated side phenomenon. One of the most famous theoretical results is Hawking radiation. When quantum field theory is applied to curved spacetime near an event horizon, black holes are predicted to emit thermal radiation. The crucial scaling is inverse with mass. Smaller black holes radiate more strongly, larger ones far more weakly. This means astrophysical black holes evaporate extraordinarily slowly. In principle they lose mass, but in practice most known stellar and supermassive black holes gain more energy from their environment than they lose through Hawking emission. Even the cosmic microwave background contributes incoming energy. So Hawking radiation is profound for fundamental physics, thermodynamics, and information questions, yet it does not make ordinary observed black holes vanish anytime soon. The timescales for large black hole evaporation are vastly longer than the current age of the universe. Because black holes emit no light from within the horizon, detection depends on indirect signatures. The most familiar is the accretion disk. Gas spiraling inward becomes compressed, turbulent, and intensely hot, radiating across the spectrum, often strongly in X-rays. Friction and magnetic effects convert gravitational energy into light with remarkable efficiency. In active galactic nuclei, these processes can power quasars, among the brightest persistent objects known. Another method is stellar dynamics. By tracking the orbits of stars around an invisible center, astronomers infer the enclosed mass and compactness. If enormous mass fits inside a tiny region with no luminous alternative, a black hole becomes the best explanation. This is how Sagittarius A* was established. In modern astronomy, the invisible becomes measurable through motion, heat, and radiation signatures. Gravitational wave astronomy added a new detection channel and transformed confidence in black hole populations. When two black holes spiral together and merge, they generate ripples in spacetime that propagate outward at light speed. Detectors measure tiny length changes caused by these waves and reconstruct masses, spins, and merger energy. This method is powerful because it does not rely on light at all. Even completely dark mergers in dust-obscured or distant environments can be observed through gravity alone. Waveforms match general relativity's predictions with striking precision, providing direct tests in the strong field regime. Repeated detections show that black hole binaries are common and that merger remnants can be substantially more massive than typical stellar black holes. Gravitational waves turned black hole study from rare case inference into a high-volume observational science. So what should we conclude? Black holes are not magical cosmic monsters, and they are not speculative placeholders. They are rigorous consequences of general relativity, supported by multiple independent observational techniques, accretion signatures, orbital dynamics, quasar energetics, and gravitational wave mergers. The event horizon defines a causal point of no return. The singularity signals where classical theory likely needs quantum completion. Stellar collapse explains many black holes, while accretion and mergers build supermassive ones over cosmic history. Hawking radiation connects them to quantum physics but is too weak to dominate most real astrophysical systems today. In short, black holes sit at the intersection of gravity, thermodynamics, quantum theory, and galaxy evolution. Studying them is not just about extreme objects, it is one of our best paths toward a deeper, unified understanding of the universe. If you found this helpful, please like this video and subscribe for more explainers.